Antioxidants are increasingly popular, both in health food products as well as in supplements. Now, these antioxidants are intended to eliminate reactive oxygen species in our body. These reactive oxygen species are produced from the normal oxygen that we need in our body, but they can then go on and react with other molecules in our body and cause dangerous damage that could potentially lead to disease. This includes damaging our DNA, which of course could potentially cause cancer. Now, reactive oxygen species are an example of free radicals. And of course, as we can see with our reactive oxygen species, these are quite dangerous in our body because of the wide array of different reactions that they can have. However, in organic chemistry, this makes our free radicals quite useful. So they're highly reactive. They can react with things such as alkanes that we don't normally see reacting under most of our standard conditions. So what is a free radical? A free radical is simply an atom or a molecule that has a single unpaired electron. So here we have our bromine atom, and if we just have a single bromine atom, we of course have our 7 valence electrons, and that single electron which would be unpaired, which would make our free radical. This single electron is going to want to react. Again, of course, our bromine wants a full octet. We also don't generally want unpaired electrons. So we're going to be very reactive as we're trying to gain that extra electron or give away that electron so that we no longer have our single unpaired free radical. Now, if we want to form a free radical, such as our bromine free radical here, we're going to do this using a process known as homolytic bond cleavage. Homo, of course, refers to something that is the same. It's uniform. Lytic just refers to bond breaking. So if we take something like diatomic bromine, right, which is the normal molecular form of bromine that we find, we don't normally see just our bromine free radicals sitting around. They're usually going to be bonded together so that they each have that full octet of electrons. Now, typically, of course, what we've seen with molecules is we've seen heterolytic bond cleavage, right? So heterolytic bond cleavage would be if we have our bond, and we show an arrow, of course, going from our bond to one of our atoms, indicating that both electrons from our bond are breaking and going to that single atom here that's indicated with our arrow. So our product here would be one bromine with an extra lone pair of electrons to get a negative charge, and a second bromine that would be missing electrons and would have a positive charge. So this was heterolytic bond cleavage, and of course the hetero here is referring to the fact that we have an unequal or uneven distribution of electrons here, since one bromine took all the electrons and the other bromine lost all of those electrons. So our homolytic bond cleavage, we're going to take one electron and put it on one bromine, and another electron and put it on the other bromine. Notice here, as I'm drawing these electrons moving out of our bond, I'm using arrows with just half of an arrowhead here. Right? So our normal curved arrows with a full arrowhead indicate 2 electrons moving, whereas here with our half arrowheads, this is just 1 electron moving. So we start off with 2 electrons in our covalent bond. We have 1 electron coming over here to our bromine on the left, and 1 electron coming over here to our bromine on the right. So our end product then would be 2 bromine free radicals. So each of our bromines from our diatomic bromine get that single electron to take them back to the 7 valence electrons with that 1 unpaired free radical electron. As I mentioned earlier, our free radicals allow us to have reactions with compounds that we normally consider relatively unreactive. So of course, the greatest example of this is our alkanes. right? Previously, we've only really talked about combustion for our alkanes. But now, with our free radicals, if we take our alkane and combine it with a diatomic halogen, specifically bromine or chlorine are generally used for this purpose. So our diatomic halogen, of course, can break apart using our homolytic bond cleavage to form those free radicals. And that free radical will then react with our alkane, add on to create a alkyl halide. We'd also get a hydrogen halide produced from the other unit of our halogen. So, we're going to take a closer look at the mechanism of this reaction so we can understand what our free radicals are doing here and how this reaction will proceed. Our free radical reactions are actually going to have 3 different steps for every free radical. It will have an initiation step, a propagation step, and a termination step. Our free radical reaction mechanism starts with initiation. So initiation is the reaction step where we actually form our free radicals. So we're going to show the same homolytic bond cleavage that we saw before. So here we have our diatomic bromine. And of course, as we saw before, we can show the 2 electrons of our bond splitting up with 1 electron going to each of our bromines to create that free radical. Again, we have our half arrowheads here representing single electron movement. Now, our diatomic halogens are actually uniquely suited for this initiation step. So when we want to have homolytic bond cleavage, there are 2 key things that we need. One, of course, we want our bond to be weaker. Halogens do tend to have weaker bonds since they tend to be larger atoms. We also want a bond that is purely covalent, right? So if we have 2 atoms that are equally sharing their electrons, then it's more likely that those electrons are going to split apart evenly when we break that bond. If you have something like a hydrogen-oxygen bond, of course, as we know, our electrons will actually be pulled over closer to our oxygen, giving our partial negative and partial positive charges. And so it's always more likely that this bond will break in a heterolytic bond cleavage, right? So if we have something that's purely covalent where they're equally shared, it's more likely then to break apart, as opposed to our polar covalent bond over here. Once we have our free radical formed, we can then proceed with propagation. So in our propagation step, we're going to be starting with our free radical. Again, of course, this is our highly reactive compound that's going to allow for this unique reactivity. And in this case here, of course, we're reacting with our relatively unreactive alkane. So here's our alkane. Of course, we have hydrogens here. And normally these hydrogens, again, are relatively unreactive, but our bromine really wants to get an extra electron. So it's going to come in here, and it's going to cause this bond to break and dump its free electron onto our carbon. Right? So we're taking an electron from this bond, an electron from our radical, and forming new bonds, and then the other electron from that bond is going to our carbon. So our products from this first step here of our propagation phase would be HBr, our hydrogen halide, as well as an alkyl radical. So we get this alkyl free radical here. Now notice, of course, HBr is already one of our products here. So our products actually form in this propagation step exclusively. So they actually form kind of in the middle of the reaction, not at the end of the reaction in our final termination step. You'll see in a minute why that is. Once we have our free radical here, our alkyl radical, this can react with a second unit of our diatomic halogen. So here's our diatomic halogen Remember, of course, this bond is quite happy to break apart in that homolytic fashion. So we bring in our single electron, and we take one of the electrons from that bond to bond to our free radical, and the other one goes, and it's going to be forming a new free radical. So after the second step, we're going to produce our alkyl halide product, and we also produce another bromine free radical. So note that single lone electron unpaired, that creates our free radical. So here now we see our second main product. So that's our product right here, our 2-bromobutane, that is our primary alkyl halide product. Now what you should note here is after these two steps of our propagation, we've created a bromine free radical, which is exactly what we started with here at the beginning of our propagation phase. So this propagation phase is actually a chain reaction. And of course that means that, so chain reaction is just a reaction that can continue to occur. It produces its own reactant. So it can just cycle on and on continuously as long as we have alkanes to react with. So with just one bromine, right, we have a single molecule diatomic bromine react and produce 2 bromine radicals. We can then take that bromine radical, react with our alkane, we produce another bromine radical, and we can again react with another alkane, and we can just keep reacting continuously because we keep producing more of our reactant here. So this is what makes these our major products, right? Because we're going to see a lot of these products produced since this step will repeat over and over again in this chain reaction cycle. Now you might ask, what's going to stop our reaction then, if this propagation step can continue endlessly? Well, obviously, of course, one thing that could stop it would be running out of reactants. We do have a limited amount of our alkane. We also have a limited amount of our halogen. So you can eventually see those run out and prevent you from producing those products. But the other way to stop this reaction is through a termination event. So termination is the third and final stage of our free radical reactions. A termination event will always involve 2 free radicals running together. So they'll combine together and form one product that is not a free radical. Right? So in our initiation step, we started with 2 free radicals, So in our initiation step, we started with no free radicals, and we broke apart our bond in a homolytic bond cleavage to get 2 free radicals. In our propagation step, we start with 1 free radical, and we end with 1 free radical. And then in our termination step, we're going to start with 2 free radicals. So we might have 2 of our bromine free radicals that are produced recombining together to make our diatomic bromine. So that would look like this, where we have our 2 bromines and our 2 half-head arrows come together to form our Br2. But of course, we also have other free radicals that could potentially run into each other as well. Right? So any of the different free radical species that we produce, our alkyl radical, our bromine radical, they can all potentially run into each other and produce different termination products. So we can have our bromine radical running into our alkyl radical. So that would look like this. And it would actually produce another unit of our alkyl halide. Or we could even have 2 of our alkyl radicals running together. And of course, that would lead to then a larger alkane. So we have both of our single alkane units, and now they're combined together with a bond here where our two free radicals were, and we're actually producing a larger alkane. Now note, for all of these are going to be minor products. And that's because it's relatively rare that our free radicals will run into each other, right? So we're going to have a relatively small amount of our free radicals, since they're only produced through this initial initiation event, and then of course reproduced through our propagation. Whereas we'll have lots of our original diatomic bromine and our alkane, right? So there's lots of those floating around, so it's likely that our radicals will run into non-radicals and react to produce our major products, and it's relatively unlikely that our radicals will run into each other, and so we'll produce relatively small amounts of these other minor side products. So when we think about things like antioxidants, what their main goal is to encourage this termination event. So many times those antioxidants will actually react with free radicals. Again, those would be our reactive oxygen species, our free radicals that we find commonly in the body. And so they would react with those and terminate them and prevent these sort of chain reactions of propagation to continue and produce those dangerous products. So if we want to stop the reaction, we want to encourage termination. If we want the reaction to continue, we encourage our propagation. We want a lower concentration of free radicals, just enough to keep this chain reaction going, but not enough that they're running into each other and terminating and ending the reaction. You might notice here that I specifically showed our product as forming at the second carbon here to make our 2-bromobutane. But you might ask, well, we have lots of hydrogens here, including hydrogens at the first carbon. Why doesn't our bromine react with those hydrogens to produce our 1-bromobutane product? Right? So we could also react here in a propagation step and create an alkyl radical with a radical at the first carbon, and then that would lead to an alkyl halide with our bromine at the first carbon. To answer this question of the selectivity of our halogenation reaction, we need to look at the stability of our alkyl radical intermediate. So in our free radical halogenation of butane, we have two possible alkyl radical intermediates that can be made. We can have our primary alkyl radical, where we have our radical reacting at the first carbon to produce our free radical electron there. Or we're going to have our secondary alkyl radical, where we react at the second carbon and form our free radical there. Of course, we can also react at the third or the fourth carbon, but those would produce the same structures. Now, as we look at the stability of these intermediates, we're going to use a similar reasoning to what we've seen before with our carbocations. So when we have a free radical, our carbon, of course, is now only going to be bonded to 3 different items. Right? We have our 2 carbons and our hydrogen, so that means that we're going to be sp2 hybridized. So we have our p orbital sticking up and down, and then we're going to have our 3 sp2 orbitals going out all in the same plane, our trigonal planar shape, one to the back, one to the front, and one straight off to the side. So this would be going to our other carbon. This would be going to another carbon over here. And the last one, of course, would be going to our hydrogen right here. So, within our p orbital, we're going to have just our single unpaired electron. Now, previously, of course, with our carbocation, we would have just an empty p orbital here. And what we saw is that that empty p orbital could actually partially overlap with the p characteristic of our adjacent sp3 orbitals on carbons. So we can actually get this partial overlap here or this hyperconjugation, we call it. So our hyperconjugation will occur here, where we have this partial overlap between our p orbital with our single free radical electron and our adjacent carbons that can actually partially overlap using their sp3 orbitals. For each carbon that we have adjacent to our free radical carbon, that will be additional orbitals that can partially overlap, and it will then add additional stabilization for that free radical lone pair or unpaired electron. So essentially we're able to kind of share out that free radical electron. So each of these carbons will kind of be taking a share of that electron in kind of a partial double bond almost. And so we don't have to just have that single carbon with its associated instability, that single electron just shared on that one carbon. So our overall stability then will be greatest for a tertiary carbon, right, where we have 3 other carbons that can share the instability of that free radical electron. Then of course we would have secondary, and of course primary, and our single methyl carbons. So going back to our reaction, this primary free radical on the left would be less stable and therefore less likely to form, while this secondary free radical on the right would be more stable and more likely to form. So our 2-bromobutane would be the primary product. We would see some 1-bromobutane forming, but it would be less prevalent than our 2-bromobutane. Right, so this would be another minor product that would form in addition to our major product of that 2-bromobutane. Now I should mention that this selectivity effect is somewhat limited. So for bromine, we will be somewhat selective towards our more substituted carbons, but again, we will still see some of our other carbons show up. For chlorine, actually, our chlorine will see very little selectivity. So our chlorine is actually somewhat more reactive in this free radical reaction, and so you'll see equal amounts of the 1-chlorobutane as well as the 2-chlorobutane. So since it's more reactive, it's kind of less affected by this difference in stability, and so you don't really see that same selectivity. This can lead to some problems then in our free radical reactions. So we might want only one of these products, but both will show up. So it can be a little bit difficult to select which alkyl halide product you want from your free radical halogenation reaction. So what we see here overall is that our free radicals, again, will allow us to produce things from compounds that we normally consider to be very unreactive. This can cause significant problems in the body when we then have our compounds that we don't want to react, like DNA, reacting and then breaking down, leading to potentially cancer and things like that. But of course, as long as we're able to control it to some extent in the lab, this can actually be incredibly useful. So it's a very useful reaction in the lab, but also a somewhat dangerous reaction because it is so reactive.